Alright, so I'm going to give a brief introduction to Chapter 3, which is Soils Exploration. So Chapter 2 discussed the properties of soil and the valuations of those properties. Chapter 3 is going to talk about evaluation. It's going to be going out to the test site and testing the soil out there. Exploration of it, meaning boring, sampling, testing, recording of the field exploration. So although there's different types of soils tests are discussed in the book, the lab manual has step-by-step procedures. So recognizance is a preliminary examination of the survey of a job site. Usually that information on the area. So we can look at maps or area photography. They're already available online. So we can look at that surface conditions and get our general idea of what could be underneath. Tomorrow I'll show you the GIS and show you that we can look at the different soils. They've got the whole all of Cumberland County classified, and then we've got soils books on Cumberland County and Hope County that give us in-depth information about the soil. So we can actually look at some of the campus where we took our soils exploration from. So we can simply do that by going to some aerial photography, GIS, that's already online. So that's good, good, easy to kind of tell what's going on. Topographic maps are another good way of getting information. So these are all usually online. We can actually get some information from them, but you also want to go out and visit the project site. So let's just say when I'm going to survey, look at somebody's property survey, I'm going to look at it online first. I'm going to go to Google Earth. I'm going to do GIS, put the aerial photography on there. I'm going to get as much information as I can, but I'm not just going to give them a price based off that without going out there. So on site is the best way to be able to see what you're getting involved with. Of course, we might not, can understand what we're going to get involved with underneath because you can't see that, but you can get some idea from just visiting a site. So that's some ways that we can do stuff ahead of time before we go out there, but you want to do an on-site evaluation. All right, so steps to doing that. There's we're going to be looking at, there's going to be 3 ways that we're going to do it. Soils exploration can be thought of consisting of 3 steps. We can bore, we can sample, and we can test. Before the boring refers to drilling or advancing a hole in the ground. Sampling refers to removing the soil from the hole, and testing refers to determining characteristics. So we haven't bored anything, but we do have the capability to do it. We've got bores over in the lab where we can try to get a spool sample and try to get it most undisturbed as possible. We definitely did sampling. So we got some out, we put it in a container, we tried to keep it dry even though it was disturbed, and then we brought it in to do our soils testing on that. So boring could be, boring are some of the most common types of boring would be an auger, wash boring, test pits, and core borings. So an auger would have like a screw type tip in it, and you would try to bowl down. So, and there looks like a bore auger. So in other words, you need some machining. Usually a lot of times these bores would go like 100 feet deep. And I know a lot of your geotechnical firms will do that. When I was doing the surveying ahead of time they were wanting to do like an overflow parking lot behind Goodyear for 18-wheelers. But they had to see if the soil could withstand that. So we actually had done surveying, and they had some soils tests done and augered down and found out that it wouldn't be able to withstand the loads that they were going to have on it. Even though there was no wetlands, but it still was low, kind of wet land. I call it wet land. I got wet, I'll put it that way. So test pits are expensive, but you can dig down with a test pit with the backhoe bulldozer. They're generally bulky, expensive. They're limited to shallow. Nevertheless, they can have some advantages. One is that you can get in there and you can look at the different layers. You can actually see the layers. When y'all were digging down over there in your test pits or your little holes, you could see that it changed from like a sandy clay to a clay just by the color. And so, getting in a pit and digging a pit out, you can actually inspect it. You can take color photographs of the soil. It's in its natural condition. Another advantage that you can be used is to obtain undisturbed samples. So it's kind of, I'm going to show you their little test pit here. So there they've got a test pit. They can kind of look at the 3 different layers. They can get in there. They can dig that out with the backhoe and get down in there and kind of look at it. Now you don't want to put any shoring up. If it's really, really deep, it can cave in on somebody. But we're trying to look at the layers. So we're trying to be able to see what we've got. So we want to dig it big enough to where we can get in there and take the pictures of it and see what's going on. Alright, so I'm going back up. So core borings are usually a drill. And basically for rock, they're often done using a diamond core drill and a drill in a core barrel sampler. So in other words, we do have rock. There's bedrock beneath, everything on the earth. Especially if you're trying to put a multi-story building, you're going to have to get your borings deep enough down to get to that undisturbed or that underlying rock layer to be able to find out and do some testing. So you would have to do core borings. So it's a drill bit. It's usually like diamond. It's going to rotate while the water is simultaneously being pumped into the rods and barrel. This core, it can be removed, and then you can core in there and examine it by bringing the barrel to the surface. So in other words, it would try to spin in and it would collect the sample in the center of it, and then you could pull it up and open it up. And so obviously the more borings made, the better the analysis of the subsurface conditions should be. So borings are expensive, and however, and a balance must be made between the cost of additional borings and the value of the information gained. So there's usually a rough guide. So there's not really a specs, but there's a rough guide for spacing of the borings. So the following ones are, if it's a multi-story building, you might want to do your borings every 50 to 100 feet. If it's a one-story building and maybe earthen dam and borrow pits, you might want to do them every 100 to 200 foot. And for highway, and it's just the subgrade for a highway, they would be every 50 to 1,000 feet. And the spacings may be increased if you found out the soil conditions were uniform. So in other words, if you keep getting the same conditions, then you may be able to increase it, but then also it may have to be decreased if there's some if it's found it's non-uniformal. So once the means of the boring and spacing have been decided, then the final question comes up, like, how deep do you want to do it? How deep do we want to do one for a building or a highway or a strip fitting? So again, here's the test pits. So we want to kind of look at, is the soil acceptable for bearing the capacity to encounter, a shallow depth? Or do we need more borings to go beneath that to figure out what the underlying material is? In the case of a very heavy structure in school, including tall buildings, boring is the most case should extend to the bedrock. In all cases, it's advisable to investigate drilling at least one boring to the bedrock. So there's now, the new book does not have these figures in here, but I really like to include these figures and actually had the extra data in Blackboard already, because if you're not sure and you're kind of new to it and you're trying to get some idea of depth to do your borings, this is a really good, they have 3 different charts that we can use to figure that out. So figure 3.6 is for a continuous footing, such as a wall footing. So you'll typically see it's not for a heavy building, it's not a square load, it's usually a wall footing, something maybe that's underneath like a slab on grade, but it's what you would say continuous. So if I give you something and it says wall footing, you want to use figure 3.4, and I'll show you what it looks like. This is 3.4. So I actually highlight that because 3.4, and I put wall footing. So in other words, we would have the unit weight of the soil, and we'd want to figure out what our pressure needs to be, like how much PSI can it take. Then we could actually determine what the width of the footing is, and where it crosses over, we'd be able to determine our boring depth. And I'll give you an example of that. All right, so figure 3.5 and 3.6 are for square footings. So if it gives you a square footing, like a building, slab, something that is square, not just strip, we would use 3.5 or 3.6. The difference between the two is that the square footing for 3.5 has pressures from 1,000 to 9,000 pounds per cubic foot. So in other words, that's high pressure. For lower pressure footings, and you might have 1,000 or 100 to 1,000. So a lot of times when we're doing concrete, like we're going to do a concrete slab, and we were going to do it out to put a building on it, and our PSIs, typically you're looking at 3,000 pounds per square foot. So just to give you an idea, and that's for a prefab building, just some ideas. So 1,000 or 100 to 1,000, if the groundwater table is at the footing base, so I'll tell you what that means. So we're going to be looking at if the groundwater is lower than distance B, then we'll use the footing width. So it should be noted that the left side of the table in figure 3.4 through 3.6 has 2 scales and are given for footing width and minimum test boring depth. And each figure, footing widths given on one side of the width scale correlate with the boring depths given in the same of the boring scale. I'll explain that one. So as we're looking at, and there's an example, it says we have an 8-foot square footing, and that the pressure needs to be 4,000 pounds. The wet unit weight is 20, and the water table is estimated to be 30 feet. Because if the water table was less than 8 feet, then we would need to look at something different. But all the examples in the book are going to have it estimated below that for us just to get some ideas. So what we would do is that particular one tells me it's square footing. So I'm looking at 3.5 or 3.6. With the 4,000 PSI just tells me that I'm going to need to be in 3.5. So it's 120 pounds and a 4,000 PSI. So what I would do is I would draw a line from here, a straight line to here, and then extend it to this pivot line and put a dot. And then this is where they have the 2 scales. If the square footing, and this is an 8-foot square footing, if it was less than 8 feet, we would be looking at the right side of this chart. Therefore, when we're reading the depth, we would read the right side of the boring depth. So this is actually what we're determining, is this line right here, our number 5. So we have a pivot point, and this particular one was 8. So I would draw a line from the 8 to where my pivot point was, and then I would read the depth here. So because we read on the left side of this line, we would read on the left side of the boring depth. So actually, they read to be about 22. So as you can see, there's 20, 22, 4, 6, 8. That's 30. Well, there's 22. 30, 40. So if they would have said it would have been 4 feet, then I would have been down here. And if we did a pivot point from here to 4, we would actually be reading on the right side. So don't forget that pertinent information. So, and we can talk about it more in class. This is just kind of give you a reference to what's going on. So, these figures are quite useful. We can estimate the minimum required test boring depth in cohesive. So in the final analysis, however, the depth of the specific boring should be determined by the soil engineer based on his or her knowledge, experience, judgment, and general knowledge of the specific area. Also, in some cases, depth and borings may be specified by a local code or company. But at least this kind of gives you an idea that we would actually want to at least dig down to 22 feet to do a boring. So they have the 3 different ones. Of course, you're going to see this again. So sampling refers to taking the soil or rock from a bored hole. Sampling may be classified or either disturbed or undisturbed. Such samples are obviously disturbed like we did, and thus for some of the characteristics changed. So actually when we brought it in, some of our characteristics changed of our property. Disturbed samples should be in an airtight container, plastic bag example. So I had y'all putting it in the 5-gallon totes. They should be, of course, properly labeled as the date, location, borehole number, sampling depth, and such forth. Disturbed samples are generally used for soil grain analysis, determine the liquid limits, plastic limits, specific gravity, as well as other tests. So actually, you've already got to do these tests, so you kind of know what the purpose was for bringing the samples back into the office. And then for determine other properties such as strength and compressibility and permeability, it's necessary that the collected sample be exactly the same as when it existed in place, or what they call in situ, within the ground. Such a soil sample is referred to undisturbed. It should be realized, however, that such a sample can never be completely undisturbed, because exactly the same as it was when it existed in place or in the ground. So there exists a large number of tests that can be evaluated for various properties, and they include both laboratory and field, and some of the most common ones are listed under this table. So as you can see, here's some of the tests that we could do. Unit weight, consistency, grain size, which you've done, compaction characteristics. We're going to be getting in compacting. Hopefully, if I can get over through this chapter pretty quick, then we can maybe actually get to do some compaction in lab, and then maybe get to some other stuff outside, like a sand comb test. Alright, so how do I know where the groundwater table is? So the term groundwater table, or just water table, has been mentioned several times in the chapter. So section 3.4 is going to give you some detailed information and the importance to this. So groundwater table can be located by measuring down to the water level in existing wells in the area. It also can be determined by boring holes. The level for which the groundwater rises in a borehole is the groundwater evaluation in the area. If the adjacent soil is pervious, meaning it can soak up sand, the water level in a boring hole will stabilize in a short period. So general practice in soil surveying is to cover the borehole with a small piece of plywood so that you don't let animals or frogs or whatever fall in there, and then come back 24 hours and look at it, and then record the groundwater table. The hole then should be filled. So we were going to build, and we're still going to build, a about 1,800 square foot building in our backyard. And they came out here to do our concrete slab, and where we had decided, we put it on the high side of the lot, and we showed the contours, and that was the driest side of the lot. But once they came out there, the water started pumping. When they started trying to grade it and compact it, it was like pumping really bad. That means it's got a lot of plastic in it, or a lot of plasticity. So they said they're going to have to wait some to let it dry out. So what we did is we did 4 boreholes down in the yard, and the water table looked like it was maybe 2 feet below in some places. We probably could shift it left or right and it could dry up, and we're not sure why the water table was just that below it. We don't have a well, we have water. So that was our way of determining what the water table was, and trying to watch the water table. You know, if it's a drier time of the year, then the water table might drop. So we're hoping that with the weather getting hot, that our test pits, and we augered down, and some of them were about 3 or 4 feet deep, but you can see that the water table was about probably 2 feet below it, and we just kept them open. We just come through and check it out and watch what's going on, and then we'll go over there and get one of the vehicles and try to roll over the land a little bit and see if it starts pumping. So that's kind of a real life scenario on what water table means, and trying to get something stable enough for us to put a concrete pad on to be able to put a prefab building. Plus we're wanting to put a lift in there to work on cars. So tomorrow I'm going to have you, so I'm going to upload this video, and then the SPT test, standard penetration test, I'm adding a video online for that for you to watch, and then we will actually go over some of the calculations. Alright, hope y'all had a good day and a good weekend, and a happy 4th, and we'll see y'all tomorrow.